on Friday, towards the end or towards the middle, someone came up to me and told me that the homework was in fact a lot longer than what Isabel normally assigns, and I wasn't aware of Isabel assigning so little homework. I thought I was in the minority assigning such little homework, but I guess about the homework. All right, look, my rise to fame in physics in undergrad was, that university physics book you guys use. I solved every single problem in there in undergrad. So, that's how I learned my physics. So, does everyone think the homework is too much, or is it manageable? It's a lot. Everyone thinks it's a lot. Is there anyone here that thinks it's not enough or not too much? All right. I mean, I guess if it's a unanimous consent, then this is an issue I can do something about. Okay, start effective next homework. I can reduce the homework by about 25–30% across the board. I mean, it really it doesn't make too much of a difference for me. It's just more practice for you guys. And if it's too much, then I don't want to put too much pressure on you guys. I want you guys to be able to do whatever problems I assign properly, not just rush to finish all the problems. That's ultimately the goal. So if the homework is a lot, then I can reduce it. Now that I know how much Isabel normally assigns, I can tell you I won't assign as little as her, but I will reduce the load, so it's not too much, hopefully. Sounds good? All right. All right, so I mentioned on Friday that what we're about to discuss, the induction stuff, is perhaps one of the most difficult concepts, conceptually speaking. The only good news here is that it doesn't get any harder than this conceptually. From here on out, this is like your peak point. After this, conceptually, it's more or less less difficult than what we're going to discuss today. And after seeing what I'm going to show you today, if you guys think what you see is crazy, you're not alone. This is really not very intuitive, and that's what makes it so conceptually difficult. But once you get a hang of this, once you can think of this the way I asked you guys to, it's really not too bad. And actually, you guys will see it's quite elegant, and took a lot of ingenuity to come up with this stuff. When we discussed Ampere's law, I mentioned the experiments by this, I believe, Dutch guy, Ørsted, right, in 1819. What did he do? Does anyone remember? So what Ørsted did was, he had some battery source driving this, and had some current going about. The other way around, actually. Right? And he noticed that there was going to be a magnetic field because of the steady current. Right? So if the current's going this way, we'll have a magnetic field coming out of the board. Right? So effectively what Ørsted did was he connected electricity and magnetism. Right? So later, after this and after what Ampere has done, Faraday came about and said, hey, if we can get a magnetic field from a steady current, maybe a steady magnetic field will produce current. Sorry, if a steady current gives you a steady magnetic field, then a steady magnetic field should give you a steady current, right? So that was the hypothesis going in, and as you do many times in science, you start off with the hypothesis and you come up with experiments to see if you can prove it. So Faraday came up with many experiments to do this. Right? He had many experiments trying to do this, and ultimately he concluded that a steady magnetic field does not produce a steady current. One of these experiments that he came up with was this. Okay, so he had a solenoid connected to a battery, an EMF. He had a switch here and there. So initially he closed the switch, and you have current flowing in this way. And based on whatever, however you define this, let's say the magnetic field is going in this way, right? And he put another loop on top of this. So he put a loop that goes about something like that around the solenoid, and he did not see a current on that. So he hooked up that loop to an ammeter, multimeter, basically, and tried to measure the current that resulted from this, and he didn't get anything. So let's call this loop 1. Let's call this loop 2. So he didn't see any current on loop 2. So one day, as he closed the switch, he noticed that there was a current on that. Right? So what happens when you close the switch? Exactly. So you close the switch. Basically, everything is connected up. The circuit is going to start pumping. At least the EMF is going to start pumping some current. So initially, for a brief moment, you'll have the magnetic field here go from 0 to whatever magnetic field magnitude this is, right? So what is that? That's a change in magnetic field, right? So when the magnetic field changed, he noticed a current on loop 2. So I said, okay, now that's what's going to take. So he concluded that a steady magnetic field doesn't produce a current, but in fact a changing magnetic field will produce a current, right? And this was actually quite a revolutionary idea. And as a matter of fact, you'll learn in the next few lectures, this very concept drives our economy to this day. So this phenomenon that he discovered is called electromagnetic induction. So current is being induced on loop 2. Now, resulting from this, obviously there were other experiments that were performed. So now let's take a conducting wire, a loop that's closed, right? Let's take a square. Right, so this is my wire, and this has some current flowing through in this direction. Or no current yet, sorry. Right, and let's take a bar magnet. Right, this will have south pole, north pole. So the field is going to come something like this. Right? So once I take this bar magnet and move it down towards this loop, I'll see a current induced on this loop in this direction. Now, the direction that we arrive at for the current is determined by a unique property. So the direction of current we get is dictated by something called Lenz's law. What Lenz's law effectively states is that, okay, I have my magnetic field coming down here, it produces a current, right? Now this current, the direction of this current is going to be such that it's going to try to oppose that changing magnetic field, right? So I have my magnetic field coming down this way, right? This is a magnetic field due to the bar magnet. So it's going down. So in principle, I want to see, well, I mean, if it was the current that was producing the magnetic field, I would have to see a current going in this direction, right, clockwise. But in fact, because it's trying to oppose it, it's going to be the other direction. So basically, if you want to think about it this way, the magnetic field that is going to be produced, or that would be produced by this current, would be in the opposing direction to the magnetic field that's inducing the current. Right, does it make sense? So again, the current wants to oppose the change in magnetic field, and this is precisely called Lenz's law. And this is one of the most human laws in physics. It's based on inertia, resistant to change. Right? We're all a bit resistant to change. We're all trying to fight change. So Lenz's law is actually quite an extremely powerful law, if you will. And it's always powerful because it'll always determine the direction in which your induced currents will go on. This law is not a qualitative law, right? You can't calculate something from it. It merely tells you what direction it is by saying, okay, it's going to oppose the magnetic field that's inducing the current. Now, do I have the demo? No. Well, I requested a couple of demos, but they were otherwise being used, so we'll see the demos for this on Friday. Another note on the notes, for those of you who have looked at it this morning, it's not entirely complete from what I will cover in today's lecture. I didn't have time to finish it, but I'll finish it up and put it up later this afternoon. All right, so let's look at it a few more loops. So let's take some loops, right, that go around 1,000 times, doesn't matter. And let's connect this to an ammeter. Right, I want to measure the current here. Now, actually, before I even do that, let's say I want to have a battery here. Right? So this, in turn, I mean, everything is closed, so this will create a current going in this way. It's going to go around, and this will create a magnetic field, something like that. Right? So to loop creates a magnetic field. It's all simple. Now let's call this loop 1. Let's say I have a second loop to the side. Right? Now, as I move this closer, as the magnetic field through this changes, it will create a current in this. Right? Now, previously, what gave us current? We said it was a battery, right? An EMF, electromotive force. So it stands to reason that if there's current being induced on this loop, then there's also an EMF being induced on this loop, right? And we've seen prior to this, okay, that it's changing magnetic field. So the EMF induced on this, let's call it EMF E2, is going to be proportional to the change in magnetic field due to loop 1 with respect to time. And they also noticed that the size of this loop matters. So if this loop was smaller, you'd have less flux. If this loop is larger, you have more flux. So it's also, this loop, the induced magnetic field is also proportional to the area of the second loop. Now, coming back to the induced EMF, let's call that E induced, right? So we know that this is going to be equal to the induced current times some resistance. And you may say there's no resistors here. Well, the wires have an internal resistance to them. So this is effectively Ohm's law. Right? It still applies for induction. So once he came up with this, Faraday gave Faraday the idea that EMF is really a change of magnetic flux through the surface, right? So let's take a little review of what magnetic flux is. Do you guys remember what electric flux is? Yes, right? So it's not terribly difficult. So we know electric flux is now the integral of, is it open surface or closed surface? We're looking at flux. We're not looking at Gauss's law right now. Is it can or should? So let's take magnetic field, magnetic flux. Is it closed surface or open surface? I'm looking at closed surface. So flux is defined by the integral of B dot dA, right? If I'm looking at a closed surface, this gives me 0, unless there are magnetic monopoles, because you're taking that monopole, or in the case of magnetic field, you're taking the bar magnet or whatever you're looking at, and you're enclosing it in a surface, right? So the flux, net flux, will always be 0 if it's a closed loop. So when you're looking at flux, you're looking at an open surface. Right? So flux is always open surface. So this effectively is what? We're looking at the B that's perpendicular to the surface, times dA, and this is going to be equal to B, or in this case it's A once we integrate it, A cosine of phi. Now let me show you this with a diagram. So if I were to have some random surface, what does my dA vector look like? It's going to be perpendicular to the surface, right? My area vector is always perpendicular to the surface I'm looking at. So let's say this is some patch I'm looking at, this is my dA vector, and this is perpendicular to that. And let's say my magnetic field, my magnetic flux is in this direction. Right? So this magnetic flux would have some component that's perpendicular to the surface, and some that's going to be parallel to the surface. If I'm looking at a surface that's like this, let's say this surface but the side view of it. If I have magnetic field flux going through here, and this is perpendicular to the surface, right, which means that it's going to be parallel to the area, right? Yes? Okay. So that's effectively where the idea comes from. Now, as long as the perpendicular component of the field is parallel to the area vector, right, the angle between them is 0. So again, we define magnetic flux by that. So if you take an obscure shape, not obscure shape, but an obscure angle, and this, I have my magnetic field that is going straight through this way. The angle between the area vector, this is my area vector, let's say, and the magnetic flux is phi. Right? In this case, the magnetic flux I get is going to be B dot dA, or B dot A in this case because I integrated. And this is going to be B A cosine of the angle phi. If my magnetic field was parallel to the surface, then there's nothing of that field going through that surface. Therefore, the flux through that surface is going to be 0. Right? So if this phi was 0, then cosine of phi is going to be, cosine of phi is, so if, yes, you're right, 1. So if this was 90, then there's going to be nothing going, wait, is it right? That is right. No, cosine of, oh yeah, that's right, yeah. So this was 90, then the flux through that thing is going to be 0. All right, so that's a little review on flux. Now let's get back to induction. All right, so let's say I have some random surface, right? And I have a magnetic field, an increasing magnetic field that's coming out of the board, right? Which direction is it going to induce the current on this conducting loop? So my magnetic field is going this way, so I would think the current would be this way, but Lenz's law dictates it's the opposite, so it'd be going clockwise, right? So this is going to be my I going through. Like I said, this is increasing, which means that there's a change in magnetic flux with respect to time, right? So that's going to give me a current that's going to be induced. So this induced current would produce a magnetic field that's going into the board, right? If my current's going this way, then that would normally produce a current, a magnetic field going into the board. So it is a magnetic flux through this. I attached a flat surface to this, so it's my magnetic flux through this flat surface that determines EMF, and also the direction of the magnetic field determines the direction of the EMF. So EMF here can be written as a change in magnetic flux with respect to time, right? That's effectively it. Now we put a minus sign here to remind ourselves that it opposes the direction of the magnetic field, right? This minus sign is not really very important. We just put it there to stay mathematically. Yes. Would the induced magnetic field be changing? Well, changing magnetic field produces steady current, right? Steady current would produce a steady magnetic field. But usually we don't really take into account the induced magnetic field because it's going to be relatively small compared to this magnetic field. And that's, if you want to think about it, it sort of gets absorbed because it opposes it, so overall net flux is still going the direction of this, otherwise you wouldn't have the current. So we wouldn't really take the induced field into account. Like I said, we include this negative sign just so we're mathematically kosher, right? We don't want to piss off the mathematicians here. So like I said, this minus sign there shouldn't bother you. Actually, when I solve these problems, the induction problems, I don't even look at the signs. I go through, solve the problem, and then later I use Lenz's law to figure out which direction it's going in, and based on my sign convention, I assign the correct sign, and I'm done. So in this case here, if I is going this way, obviously my EMF that's produced would be this way. So we can write, okay, so this is correct. Now, what's my flux here? So I can say that this is going to be equal to negative d over dt, magnetic flux integral of b dot dA, right? Open surface. So this effectively is Faraday's law. Now we also know that EMF from a few chapters ago is closed loop integral of E dot dl. You guys remember that part? All right. So you also see everywhere you see the current in the wire, you see an electric field, right? Otherwise, there'd be no current flow through the wire. And if you go once around the whole circuit, right? So if you go once around the whole circuit, then your EMF is going to be equal to closed loop of E dot dl. And this is closed loop. Now you have to appreciate the fact that this circuit here, I'm looking at the loop of wire, has no battery, right? Everything here is induced due to the magnetic field. Now this Faraday's law is in a bit more detail than, actually we'll write in a bit more detail and then we'll So Faraday's law, we can write this as closed loop integral of E dot dl equals, now I can either write this as the change in the magnetic flux with respect to time, or simply write out the flux part. Right? I can just say it's equal to negative d phi b over dt. It's the same thing as saying negative d over dt integral of b dot dA. Open surface here. Right, so this is Faraday's law. So what do we have so far? We have Gauss's law, right, which basically says integral of what? E dot dA, right? Closed loop integral of E dot dA equals charge enclosed over epsilon naught. Right? It's my Gauss's law. And then we looked at Ampere's law. What did that say? Closed loop integral of B dot dl equals mu naught times I enclosed, right? B dot dl equals mu naught times I enclosed, or I penetrated, however you want to look at it. We also had the magnetic analog of Gauss's law. It stated that closed loop integral of B dot dA equals 0. This basically says that there are no monopoles. Right? If you had a monopole, you can take it, enclose it in your surface, and you'd get some flux that's not 0. If you guys are able to find that, come see me. We can go share the Nobel Prize. And finally, we have this. We have Faraday. Faraday's law says E dot dl. So if you go around closed loop, we get negative d over dt integral of b dot dA, closed loop. So we have our 4 Maxwell's equations. So can we celebrate? No, we can't, not yet, because we're going to go back and change Ampere's law in a few lectures. And then we can open up the champagne bottles, because we're effectively done with the course then. So the direction of dA for this is not so crucial here, because Lenz's law essentially will help us find the direction of EMF. Right? But just so we're rigorous enough on our proof, let's go through how we would go about this. So let's say I take some surface or some loop, closed loop circuit wire, and I attach, in this case, a flat surface to this loop. And I want to march around in this direction. I want to go E dot dl, right? So I want to march around this loop. Faraday doesn't say which direction we have to go. So what are we going to do? We'll go to right-hand rule as we did with Ampere. So when we're going around, if we go around clockwise, right, we'll say that dA, so we're going around clockwise, so it's this way, dA is going into the board. Right? If you go around counterclockwise, we say that dA is coming out of the board. Right? So we'll just make that our convention. And with that, now you guys are free to go and solve all the problems. Now, so what do we do so far? Once you have your loop, your circuit, right, you essentially have your surface for the most part, right? So what do? You take your loop, define your surface for it, either flat surface or, as long as it's properly defined surface, you should be fine. So once you have your surface, you have your loop, you define the direction in which you're going to go around. Right? So if you want to go around clockwise, you know which direction your dA is. Counterclockwise, you know which way your dA is. So once you do that, and once you've attached your open surface to the loop, you can determine what B dot dA is. Right? You can determine the magnetic flux. Right? Take the integral of that. You'll have your magnetic flux, and from this, you'll get your magnetic flux, and from that, you take your E dot dl, right? Take the time derivative of that, and you essentially get this, right? And then you use Lenz's law to figure out the direction. Right? Basically, you put the minus sign in there and take that into account for the direction. Right? Simple enough. Or is it complicated? It may look a little complicated, but it's actually not that difficult. Now, what time is it? Okay. Let's go back to solenoids. I mentioned they were interesting, right? Yeah, we'll be using those a lot. So solenoids, they produce magnetic fields, so they're pretty interesting here. So let's take a cross section of the solenoid. So we have all the loops there on top. So if you have our magnetic field, let's say it's coming out of here. Right, magnetic field is coming out of the solenoid. This is all my windings, my stuff for it. And let's say I put a wire around this, a closed loop around this. What's going to happen here? Remember I said the size of the loop matters? In the case of the solenoid, we know that the entire magnetic flux or magnetic field is confined to inside the solenoid here. So you can make a really big loop, the flux won't change here. It'll still be the same flux. Right? So the size of the loop doesn't matter here because the flux is not dependent on the size of the loop. But what's going to happen here? I have a magnetic field coming out of the board. Right? Let's say it's a changing magnetic field. What's going to happen? If my magnetic field is coming out of the board, then I'll have my current that's being induced going in this direction. Right? So it's going to induce a current in this direction. Now that's with one loop. Now what if I have 3 loops around? So let's say I look at a different view of it. I have something like 3 loops, and I have my solenoid that fits in there. I guess before we even answer that question, we have to think, what kind of surface do we attach to this? How do you visualize that surface? Not exactly multiple circles here, but it's close. It's sort of like spirals, right? Like a helix. So the best way to visualize this is you take this, dip it in some soap, take it out. There's going to be a film that's going to be attached to all these, and it's going to be in the spiral direction that you need. So that's effectively the surface you'll need to attach to this. Right? So let's say the surface is attached. What would happen now? We have a magnetic field, right, due to the solenoid that's in here. Right? It's producing the magnetic field. What's going on now? We know one loop produces I. What are 3 loops going to do? 3I, exactly. It's going to be 3I. So if I have 3 loops, it's going to be 3I because you'll have 3 times the flux. Right? You have flux going through this surface, and through that surface. So you have flux going through all the surfaces there. So you'll have 3 times the current, which means that you'll have more or less 3 times the EMF. Right? So if you have 1,000 loops, right, 1,000 of these loops, then you'll have 1000 times I, and then you'll have 1000 times the EMF. This essentially forms the basic fundamentals for transformers. For any of you who've been out of the continental United States or continental America, you've essentially had to deal with different voltages, right? You either had to, when you're in another country, you had to deal with 240 or 220 volts, or when you're here, you deal with 110 volts, right? And if you're using electronics in these different places, you need to have some sort of a transformer that either steps up or steps down the voltages. Precisely the same principle here. And not just limited to that, we'll briefly talk about transmission lines later, right? So when you have the transmission lines, when you have those stations, each places, they basically ramp up the voltage really high, right? So you have voltage going through the wire is really high. And then they come to the station in the end that's going to distribute everything out, step everything down, and then that gets distributed out at 110. And we'll talk about that a bit later. So from what we can see, Faraday's law is not really very intuitive, right? It's basically the opposing theory of what you would think was possible. Now, if you remember Kirchhoff's law, right? You guys have a loop, you guys go around, you sum up all the voltages, you say that's 0, right? That was enough for more or less very intuitive, right? You had integral of E dot dl. Is this closed loop or open loop? Closed. So this is equal to 0. No longer the case. As we saw there, when we march around and we do E dot dl, this is no longer 0, right? That's it's no longer 0 when we have a changing magnetic flux. Kirchhoff's law says it's 0. Faraday's law says it's not 0. Now, if you're dealing with changing magnetic flux, then the electric fields inside those loops you're dealing with will become non-conservative. Right? So you're dealing with non-conservative fields now. And Kirchhoff's law, as you saw, only holds as long as the E field conservative. Right? So when we're dealing with non-conservative fields, as we are right now, this is no longer the case. Now, to give you guys a little refresher on conservative and non-conservative fields, do you guys remember that from mechanics? When you guys are doing work, friction, all that. Friction's a non-conservative force, right? All that rings a bell. Right? Okay. So what does that mean? So if electric field is conservative, which means that if I start off at point 1 and go to point 2, basically what I'm looking at is from 1 to 2 of E dot dl. This is path independent. It means that no matter which direction I go, which path I take, I'll end up at the same answer here. Right? So basically that means that the potential between these 2 points is uniquely defined over there. This is no longer the case now. So once we go around the solenoid, you get one value. Right? Once we go around 3 times, you get a completely different value, as we saw up there. Now before, with Kirchhoff's law, if you go around once, you get the same value as going around twice, as 3 times, doesn't matter. Because over there, we were only dealing with conservative forces, or conservative fields. Now we're dealing with non-conservative fields. So this is now path dependent, it becomes. So once the path is different, you don't get the same answer here, and this no longer holds. So this is the reason why it's not very intuitive here. Does it make sense? Right. Let's take actually let's do the demo I want to show you guys, and then you guys can take a break, and we'll continue again. All right. So this was the solenoid I was asking for last time. Right. I have a normal solenoid. I have these iron filings. I have this power supply. In principle, I can plug in this power supply to the solenoid, and then you guys should be able to see the field. But before we do that, I need to I want to deal with this. Let's just use this. This works. It works well enough. All right. Something's locked over there. This rotates. Oh. Okay. We're still good. So let me turn this on. Crank up the voltage. All right, so once I sprinkle these filings, we should see the field I was talking about last lecture. Not really. What's that? Yeah, it's plugged in. It's plugged in and it's on. You can sort of see the fields inside, but I don't want to saturate this too much. Yeah, it's not working as well as I was hoping. There's definitely current in there. There we go. So you can see down here, or up here in this case, around the wires you can see the circular magnetic field. inside you see almost basically it'll conform to a straight path, and the outside just more or less stays still, doesn't do anything. Right? See that? So inside, now going out there, you can see the fields, especially on the bottom. You can see it better, but on the outside, the field doesn't change, doesn't affect it. Yeah, inside you can see, but outside there's nothing that really changes on either outside part. All right, let's take a 5-minute break and then come back. Now, for the second half of the class, I'm going to address something that will blow your minds. There's no other way to put it. It is simply going to. So, what's going to blow your minds now? Let's see. Well, let's start off slow here. Let's say I have a driving voltage, driving EMF, right? And have some resistor, another resistor comes about, right? Let's say this is R1, R2, and this is some voltage V. Now, if I were to ask you what the current flowing through the circuit is, you guys would be insulted. Right? You guys say I should put this kind of question on the exam, so that'd be easy. But I'm going to ask you guys to be a little patient with me. So what's the current going to be here? I know that Ohm's law says V equals IR. R here is in series, so I have R1 plus R2. So V equals I times R1 plus R2, which means that I equals V over R1 plus R2. Right? Simple enough. Okay, let's give this some values. Let's say this is 1 volt. Let's say this resistor is 100 ohms. And let's say this resistor is 900 ohms to make my math simple. So what's the current I'm going to get here? Voltage is 1 divided by essentially 1,000. Right? So what I'm going to get here is 10 to the negative 3 amperes, which is basically 1 milliamp. Small current, but easy. Now let's say I have point A here, and let's say this is point D. And I ask you what the potential difference between these 2 points is. So what I'm asking you here is, what's VD minus VA? Again, equally insulting. Right? You guys are experts at this by now. You guys know this stuff. Isabel went through this with you guys. You should be good with this. But again, let's be patient here. Apply Ohm's law again. So what do we get for this? We get, this is simply going to be, let's say we go around this way. I know the current. I know the voltage drop due to this resistor. This is going to be I times R2, which is going to be positive 0.9 volts. Right? Okay. Now, suppose we go the other direction. Yes, hey, this should be the same, right? Now, why would it change? Okay, but let's do it anyways. If I go the other direction, I would get, well, that 1 volt minus IR1, right? 1 volt minus 100 times I, that's going to give me, again, 0.9 volts, right? Applied Kirchhoff's law, go around the other way, it's going to be the same thing. You guys might be saying, what a waste of time. Why did I come back from break? I should have disappeared like half the class. Well, we'll get there. We'll get there. Now, suppose I attach an voltmeter here, like this. Measuring the voltage here. Measure that there. So this lead is positive, negative. So this would obviously read 0.9 volts, right? And from that I know integral from let's say d all the way around to d of E dot dl equals 0. Right? Therefore, Kirchhoff's law holds. Right? So in this case, here, Kirchhoff's law holds. Now, let's take the same circuit, but change it up a little bit. So I'm going to take the same circuit here, except what I'm going to change is I have my resistor here, resistor here. I'll take the battery out. Right, so I have my R1, R2, same values, but instead I'm going to put a solenoid in the middle. Right, that's producing a magnetic field coming out of the board, which means that the current would be in the same direction it was as up there. Right, so this solenoid would produce some magnetic flux. So this coincidentally, it just so happens that the solenoid I picked has an increasing magnetic field that produces an EMF of 1 volt. Coincidences happen here. So again, now Lenz's law dictates that the current would go the other direction, so would the EMF. Let's hook up our multimeter to this again, our voltmeter there. And this is an increasing magnetic field, and which gives us an EMF of 1 volt. Now, so which means that if I take d phi b dt at a particular moment in time, this is going to lead to E equals 1 volt. So what is my current now? Again, insulting, right? You guys know this. Still insulting for the current. So what is I? I is the same here, right? I is the same, so it's insulting again. So you guys might be wondering, why am I making a fool out of myself asking you guys all these really trivial questions now? Well, you know what, while you're at it, now this is again point A, this is point D. So let's look at what we did before, Vd minus Va. Right? So we're going around this way again, so it'd be IR2. Okay, IR2, and we saw last time that this was positive 0.9 volts. Okay, you guys already did this. Insulting, yes. Mm-hmm. Oh, 1 volt. 1 volt. Sorry. All right, now we went around this way for this. We put the multimeter there, and we measured it, and we got 0.9 volts. Now, here comes the $1 million question. What happens when I measure it the other way around? No. How would I? Over there, I have the EMF being produced by this. So when I go around, measure it the other way around, what would I get? What's there? What happened? No, multimeter, let's say I put the multimeter here. You're saying Ohm's law doesn't hold? Kirchhoff's law. It doesn't hold here. So because, what would we get here? We'd get, if we go around the other way, I'd get minus IR. So if I go around the other way, I'd get minus IR1. That's going to give me negative 0.1 volts. Right? So same circuit. One way, I get one answer. The other way, I get another answer. Right? So this is because, in this case here, Kirchhoff's law, what we saw up there, does not hold. So what do we have to do? We have to take into account this EMF. But if you go around the closed loop integral like we did from this point to this point, there's nothing to take into account here. So we get a different answer. So let's go through this and solve it a bit more with a bit more detail. I mean, you guys remember all the loop rules for Kirchhoff's law, right? Everything applies here. It's just instead of Kirchhoff's law, you got to use Faraday's law. Now, maybe some of you have already realized this, but Kirchhoff's law is just a specialized form, a special case of Faraday's law. So you learn the easy stuff first most of the time, and then you learn the more difficult stuff. Okay, so take the same circuit. We have R1, R2, my changing magnetic field, V2 here, minus, let's call it, and let's say this is my V1. Right? So what had happened before? I read that this was 0.9 volts, and this was negative 0.1 volts. Right? Two values are different. So let's look at the derivation for this. So normally what do? We use our loops. Right? So let's call these our loops. I go around this way. I go around this way. This is my loop 1. Go around this way for this. Loop 2. Go around this way for this. This is my loop 3. Now, integral E dot dl equals 0. This is my Kirchhoff's law. Applies to 1 and 3. For loop 2, I'd have to use Faraday's law, which says E dot dl equals my EMF as a function of time here. This is equal to negative d phi b dt. And this applies to 2. Again, like I said, Faraday's law always holds, no matter what the condition here is. Right? Faraday's law here always holds, whether you have a changing magnetic flux or whether you don't have a changing magnetic flux. This always holds. Kirchhoff's law only holds in a certain condition, and that's when your paths are conservative, right? Or when you don't have basically when you don't have a changing magnetic flux. So it applies for these two loops because we don't have an EMF that's induced. Therefore, we can use Kirchhoff's law over there. For this loop, we'd have to use Faraday's law. Now, you guys remember going through all this trials and tribulations for problems like this. You have your loops, you write out your loop equations, and you go through, you solve, and you get all the answers. Well, now it's no different. Let's go through all that. So let's go through, start with loop 1. Right? So what do I have? For loop 1, I have, so let's say this has some idealistic resistance, the multimeter. There's going to be some current going through that. That's going to have some small amount of resistance. Right? So, not small. In this case, it would be a really large resistance. No? Maybe small. Maybe small. Yeah. So that is going to give me I1. So over here I have I1 as a function of time. Over here I have something, let's say I a function of time. I have some different current I2 as a function of time. Just so we'll cover all our bases and then we'll figure out what those are. So I have I1 times Ri plus I1 R1 minus I R1, right? So I'm going around this way with this current, I'm going around with this current, so this is going to add up, this is going to subtract because I'm going around this way, and I'd get this equals 0 because I can apply Kirchhoff's law there. Make sense? First loop equation? It's good? Okay. So let's move on to the second loop. So what do I have here? I have, go around this way, I have IR1, right, plus IR2 minus I1R1, and of course minus I2R2. This equals, no, Faraday's law. Doesn't equal 0 here. It equals some EMF. We know to be in there, that's 1 volt at some period in time, right? So this is not 0. We're applying Faraday's law for this second loop. First and third loop, we can apply Kirchhoff's law and we're good. So that's equals 0. This equals some EMF. So far so good on that? Everyone see why this is equal to some EMF and not 0? Right? Okay, so let's look at loop 3. So loop 3, I have I2, so I2R2 there, plus I2RI. Again, this has some idealized resistance in it, minus IR2 equals, what does it equal here? This is 0, right? So loop 1 and 3, I don't have any change in magnetic flux, therefore there's not going to be any induced magnetic fields, so that equals 0 there. Now remember, it's idealized resistance, right? So it's going to be a really large resistance. So this is extremely large compared to both R1 and R2, and therefore I1 is really small compared to I2 is really small compared to I. I'm just putting these in there so there's more terms so you guys can see what exactly is going on, because when you plug in a multimeter, if you're measuring voltage, you'd have a really high resistance there. If you're measuring current, the resistance there you want to be really low because you want almost all the current to flow through there, right? And when you're measuring voltage, you want almost none of the current. So, and you have a set value for the resistance, so you can measure the voltage more accurately. And it's the inverse is true for currents. So what do I do now? I can simplify some of these equations. So I can cancel out some of the terms. So what would I get? I'd get I1 Ri minus IR1 approximately 0, right? And I, for in this one, I have R1, R2, R1 plus R2, and the other ones effectively, cancel out with those, and this is equal to EMF, and for this one I have I2 Ri minus IR2 is approximately 0. Right? Yeah. So let's assign these things. So therefore, from these, we can say, I'm not looking at the direction right now. Direction we can dictate with Lenz's law. So V1 is equal to I1 Ri is approximately IR1. For this, V2 is equal to I2 Ri, which is approximately equal to IR2. And generally, this is a side note, the resistance here, this is along the order of the 7th magnitude ohms, normally in multimeters. So that's how high resistance you're dealing with in that case. So these essentially is what you end up with, those voltages. So for non-conservative fields, as you have here, the electric potential difference between 2 points, if I have my closed loop integral E dot dl between 2 different points, it depends on the path this time. And that's where our intuition breaks down, because up until now we've done Kirchhoff's law and said, hey, it doesn't matter the path, go around any way you want, as long as you go around this whole loop, you get 0. So now that we're changing this, our intuition breaks down and it's difficult to see. And as you guys saw here, so we went from, let's say, A to D, right? E dot dl, that's what we did initially. Now if we go from, let's say I have my point A here, point D, right? Go from here to here. On that side you get negative 0.1 volts. You go from it on this side, you get plus 0.9 volts. Faraday's law doesn't have a problem with what happens here. Kirchhoff's law does. But then again, who cares about Kirchhoff's law now? You know Faraday's law, which is the more generalized form of Kirchhoff's law, or that's not a proper way to phrase it. Kirchhoff's law is a special case of Faraday's law. So what you're learning here is, I guess on some level, more true than Kirchhoff's law, because Kirchhoff's law doesn't apply here. Faraday's law always holds. So if in this case, over here, this is convenient. So this is our, this is what we have for our Faraday's law, right? So we know that this is equal to negative d phi b over dt. Now, if I don't have a magnetic flux, if I don't have a change in magnetic flux, then this is going to be 0, right? And I end up with what I get for Kirchhoff's law. So suppose we go from point D to point A back to point D, right? So we have VD minus VA for the first one. That gives us plus 0.9 volts. And we have VA minus VD. That gives us, plus minus here, gives us plus 0. Sorry, the other way around. This is right. Plus 0.1 volts. So the total is going to give me VD minus VD. That's going to be equal to plus 1 volt. Right? Kirchhoff's law here says it has to be 0 because you've gone around the whole loop. Faraday's law says that this, being our EMF generated, that's equal to you going around the whole loop. So this is no longer 0. So keep in mind, when you're dealing with non-conservative fields, it depends on the path. And hopefully, over time, you'll build up the intuition for this. Let's do a quick demo of Lenz's law, and then we can get out of here. All right. So what I have here, just 2 pipes. One of them's a plastic pipe. One of them's a metal pipe. And what I have here is a small earth magnet. So what do you think is going to happen when I put this through the plastic pipe? It'll fall through. Right? It falls through pretty fast. What would happen when I put it through the metal one? Fall through slower. Why is that? Exactly. So if we have an opposing magnetic field, it's going in the other direction, that's going to keep this thing from falling down. But of course I have gravity on my side, so that's going to still make it go down more. Right? Pretty nifty. Let's look at it again. Over here, I can't even catch it. Over here, on this side, right? So now you guys know that Lenz's law wasn't just me BSing. It was actually exists. And like I said, it will become very clear in the coming few lectures how incredibly revolutionary and important this concept is. Right? We have our all our power comes from more or less this concept. You're inducing current by changing magnetic fields. And one of my personal heroes, Tesla, I'm sure some of you guys at least know of him, he came up with the idea for polyphase induction motors. And that essentially are what are under Niagara Falls, and that's what generates a lot of the power on that side of the coast. And Tesla essentially invented a lot of things, including the power grid. And yeah, he's an incredibly interesting person, and we'll actually watch a documentary on him after the first exam. I mean, I can't obviously mandate you guys come see it, but I can offer extra credit, so I'm sure more or less more people will show up. All right, I'll see you guys Wednesday.